All right, going to do another projectile motion problem, except this time we're not going to have a horizontal launch. So here I have a cannon shooting a cannonball at 170 meters per second at a 23-degree angle. So the cannonball is going to come out, and let's pick a different color. You know, it's going to do this right here and then land somewhere over here. The goal behind this problem is I want to find delta x. How far away does the cannonball land? So first thing, you sketch a picture, done. Label the picture, done. And then I write down everything I know and everything that I'm looking for. Now here, the only difference is I actually have an x component and a y component to this velocity. I have initial velocity in the x-axis, which is going to be constant, right? And initial velocity in the y-axis, Vy, and I'm going to put another little I there to indicate initial velocity in the y-axis. So I have a cannonball, it's shot from ground level, and it lands at ground level. Neglect the maybe half a meter or a meter tall the cannon is. Don't worry about that in this problem. And it's shot at an angle, so I have an initial velocity in both the x and the y. So in the x-axis, once again, always constant velocity, Vx equals something. Let's get back to that. Delta x is the end goal, and I don't know about time just yet. In the y-axis, initial velocity in the y equals something, and I can calculate that, but we're going to get back to that here momentarily. Tell me what delta y is going to be. Think about that for a second. Delta y here, it starts at ground level, it ends at ground level, so delta y is going to be 0 meters. So 0 meters there. Let's see, I know the acceleration in the y-axis. It's always the acceleration of gravity. I'll call downwards negative, so negative 9.81 meters per second squared. And I don't know time, and I don't know the final velocity in the y-axis. Now I'm looking for delta x. First, let's figure out what the initial velocity in the x and the y is. So think about this. Here, I have a little triangle going on, right? Here's the hypotenuse of the triangle, or the vector. Here's the angle the vector is at, measured relative to 0 degrees. So going off in your head should be a little alarm bell saying components, components, components. The x component is the vector cosine the angle. So this will be 170 cosine 23. Also check it out, the 170 has 3 sig figs, but the cosine 23, that only has 2. Y component is going to be 170 sine 23. So now going directly from my goal, in the x-axis it's always constant velocity. Vx, there is no initial and final because it's constant, equals delta x over t, right? I know the delta, I know the Vx, it's 170 cosine 23, and I'm just going to leave that in math terms right now and get it here in a second actually as a number. Delta x over t. Well, now here's a problem. I don't know time. I need to figure out what time is. Where can I go get time from? The answer is the y-axis. So let's pick a variable, or let's pick an equation using the 3 things that I know. Initial velocity in the y-axis, that's the y component of the initial velocity of the cannonball. The displacement in y, it goes up, it goes back down, right? So displacement, final minus initial, right? That's all that matters, not the path it takes. It starts and stops at ground level, thus the displacement 0 meters per second. Gravity is what pulled it back down. I can use that information to solve for time, and I actually want to use the equation that I've been using this entire time. Delta y equals VIT plus 1/2 AT squared. All right, so I went ahead and plugged into my calculator what the 170 cosine 23 is. It comes out to be 156.49, and 170 sine 23 comes out to be about 66.42. So now I'm going to plug in to this equation right here. Let's move it down to give myself a little bit more space and solve for time. So delta y is 0 equals, in parentheses, 66.42 t plus 1/2 negative 9.81, squeezing it in, t squared, right? Okay, now that's all equal to 0. This is actually a straight factoring problem now. 0 equals t times 66.42 plus 1/2 times my 9.81, negative 9.81, right? Let's slide that negative in there. T. So close those second parentheses. In fact, I'm going to come back and I'm going to make those brackets so we can really see here what's happening. So in other words, I factored out the t, right? So the t squared that was here now becomes t, and this t is factored out. So I pull a t out from both things, right, to get t on the outside times that. Now, whenever you factor, just like all the other factoring you've done, you can set up whatever's on the left-hand side of the equation equal to the two different factors. So that means t equals 0, and 0 here is going to equal 66.42 plus negative 4.09. Let's get my pen back here. Negative 4.09 t. More on the why the t equals 0 here in a moment. So now it's just algebra. So I work the algebra around, right? Subtract the 66.42, divide, and you get 16, or divide by the negative 4.09, and you get t equals 16.24 seconds. So now you might ask, well, hold on, I've got two times. Time equals 0, and time equals 16.24. And I'm going to say, yes, of course you do. Logically, this should make sense. Because if I'm considering the cannon, the launch point of the cannon, to be on the ground, right? And so y equals 0 here, and y equals 0 over here, and it goes up, right, and then curves back down, the cannonball, that is. There are two times when the cannonball is at y equals 0, the ground here. One is right before it launches, when time is 0, t equals 0. Another is after a lot of time has passed. It comes all the way up and arcs all the way back down. So here, over here where it's landing, would be t equals 16.24. And right before it launches, y equals 0, that would be t equals 0. Now let me remind you, the entire point of this problem is to find delta x. So the reason I solved for time was so I could take that time and plug in. So here it is. This is the time I'm going to want, right? This is the time associated with the landing, which is associated, you know, how far it went, right? How far away did it land? So I'm going to use this time right here. I'm going to plug it in for t. So now, I've got 156.49. Remember, that's what we solved earlier. 156.49. That's the 170 cosine 23 equals delta x. Get a good x going on there, divided by 16.24. 24. Multiply both sides by 16.24, and I get 2,000, let's get back to red here, 2,541 meters. Now, that's a long ways, but this is a cannonball we're launching here at 170 meters per second. Of course, it should be going a long ways. Now, let's actually put that with sig figs. In the original problem, right, I gave this number 170 meters per second with a decimal, 3 sig figs, but the angle only had 2 sig figs. So I only get 2 sig figs. That, and I'm going to change this around to kilometers here, delta x equals 2.5 kilometers, or 2,500 meters. All right, another question that you might find from a problem like this would be, what is the maximum height that this cannonball rises up to? Delta y max, okay? What is the maximum height? Which would occur, obviously, in the very center of the arc right there. What is the maximum height? So you draw a picture. You write down everything you know, and then you start writing down, you start grouping all your variables. So in the x-axis, Vx, right, is the x component of the initial velocity, and I purposefully chose the same thing, but we'll actually go through the process of writing out 170 cosine 23, right, because that's the x component of this initial velocity that's at an angle of 23 degrees. Delta x, we actually know from the previous problem, but you actually aren't going to need that to solve this. I'm just going to leave it blank. We also know the time it takes for it to land, but that's not the time it takes for it to reach the maximum height, right? So we can't use that time. Trick with that, but I'll let you try to figure that out. Now, Vy, initial, right? So Vy initial is 170 sine 23. I know the acceleration of gravity, negative 9.81 meters per second squared. Now let me talk about this for a second. Notice this has a negative sign. Acceleration of gravity goes down. Notice the initial velocity in the y is positive because which way is this cannonball rising or falling? Well, it's rising upwards, right? It's going up. It's not coming down. So it should be positive and gravity should be negative. Let's see here. We are looking for delta y, right? That's the end goal, delta y, and I'll write in here max, right? That's the end goal. I don't know time. But there's one other variable I know. At the maximum height, think back to free fall here. At the maximum height, if you throw a ball straight up in the air, the final velocity in the y-axis, and let's get my notations the same as earlier. Let's see, so V, Y, F. The final velocity in the y-axis is 0. Even though at this maximum height right here, the cannonball is still going, it's now only going to be moving with an x component velocity, Vx, which is constant, right? So it's still going to be 170 cosine 23, right? Whatever that comes out to be, look back in your notes for that. But the y velocity now is 0. The cannonball is slowing down in the y component, in the up and down part as it rises upwards. Gravity is stealing y component velocity until finally the y component right here at the maximum height is 0. Now you actually have enough information in the y-axis to solve for this directly. So 170 sine 23 comes out to be 66.42. You pick an equation, the equation that's going to work here, because you know the final velocity is Vf squared equals Vi squared plus 2a delta, and here delta y. You plug in what you know, and then you solve. Square my 66.42, subtract it over to the other side. 2 times negative 9.81 is negative 19.62, and then divide. You come out with 224 approximately meters. So with sig figs, because of my angle, 220 meters would be the final height. Notice I did not need the x-axis to get the maximum height here that the cannonball would rise to, simply because it's just a free fall problem. I only have to deal with one of the axes.